So our next speaker is Shih-Chii Liu. She received her BS from MIT and PhD from Caltech. She is currently a professor at the University of Zurich, Switzerland, and co-directs the Sensors Group at the Institute of Neuroinformatics. Dr. Liu is the current chair of the IEEE Swiss CAS/ED Society.
I'm good, okay.
She is the general co-chair of the upcoming 2020 IEEE International Conference on Artificial Intelligence, Circuits, and Systems. It's also known as AICAS 2020. Welcome, Shih-Chii.
Yeah, thank you. Thank you, Corey, for the introduction. Thank you, everybody, for being here today. So I want to talk about TinyML, but particularly on TinyML audio algorithms. And the reason for looking at how you can process some of these algorithms on the edge is because there's a whole lot of application domains in which you would need this capability. And so you can see, for example, in places like smart homes, smart city, mobiles, robots, etc. And also the kind of tasks that you would do when you're talking about audio TinyML. And so this is a set of tasks which involve auditory scene classification, voice activity detection, if you're talking about speech, keyword spotting, speaker verification, recognition, enhancement, and also speech recognition. And also given that there are a lot of audio devices that you see nowadays and which will continue to grow throughout the years, for example, with earbuds and audio assistants that you have at home, I think this is going to become key in looking at how you can build accelerators for audio TinyML. So I'm going to skip over this outline because I'm actually going to talk through some of the stuff. So the first thing is about the system requirements for TinyML Edge Audio. And so the points that you've already heard from the speakers before is about latency and power. So latency, because you have to make decisions without the cloud. But latency in audio also is a bit difficult because when you talk about latency for audio, if you're doing something like speech enhancement, you have to give back the, say for example, the cleanup speech within 15 milliseconds. Otherwise, the listener will get irritated, right? So it's a little bit different from just making a decision based on some classes that you might want to recognize. Low power, yes, you always want to have always on devices. A small footprint memory compute. So you want to keep this local, again, for low latency and low power reasons. There are many ways in which you can cut down on the memory. You've heard some of it from the speakers before. You can quantize the parameters, but you can also train your network so that you can have sparse weights and also sparse activations, because that also cuts down on the computes that you have to do when you're running the system. And also high accuracy is actually quite important because even though you can train a network, say using a particular data set, it doesn't mean that it's going to run well when you actually deploy it in the real world. And so audio actually is quite difficult because it's a non-stationary signal, and also your room acoustics matter a lot. And it's very hard to train a network that can perform well in all these different conditions. And so you might be able to train a small network that works well with a particular data set, but it doesn't mean that it's going to work well in just any scenario. And so privacy, again, is a concern. So that's why you want to keep the locality of the computation. And also the other thing that I think is very interesting, the next, actually currently and also in the next few years, is this thing about adaptation and lifelong learning. And because you can't learn on everything within your data set, you want to actually have a network that can adapt to new acoustic conditions. For example, recognizing when a new speaker comes in and you still want to do keyword spotting on that speaker, and that speaker happens to have, say, an accent that wasn't part of your data set, right? And so you want to basically do incremental learning, if you like, so that you can recognize that speaker. Okay, so I show here a set of networks that have been proposed for the different speech tasks. And so they're basically going from voice detection, keyword spotting, all the way down to speech recognition. So this table gives you an idea of multi-layer perceptron recurrent neural networks. And you can see that they vary quite a bit. So first, you have different architectures. For example, here's one that just uses fully connected layers, has a very few number of parameters, and they can go up to very large networks that use recurrent neural networks with LSTM units, and now with more parameters. And you see this because these different networks are trained for handling different data sets, or for example, for voice activity detection, it could be that you want to have a high accuracy under different SNR conditions and maybe a wide range of SNR conditions on top of that. In that case, your network has to be much bigger to work well under those conditions. So I have to go back. Okay, now if you increase the complexity of the task, then you can see the networks generally become bigger. Even for the small networks, the number of parameters grow. And also for the large networks, the same thing happens. And again, you see this whole kind of zoology of different kinds of networks. And so if you're a hardware person and you want to build an accelerator, you have to take all this stuff into consideration because which architecture are you going to use in the end when you build the chip. Then the other thing also I wanted to show is there's also CNNs that have been proposed for TinyML audio task. And these are two examples for keyword spotting and speaker recognition. Again, they're small networks and large networks. And they usually consist of a convolutional layer followed by fully connected layers that are linear or nonlinear. But in general, you can also see the number of parameters are lower compared to the RNN. Now, so there's trade-offs between these different DNN architectures. So multi-layer perceptrons are nice because they have a small footprint, quick to compute, easy to train. But the disadvantage is you always see that the performance gain is limited if you benchmark this particular architecture on a particular task. Now, if you look at convolutional neural networks, they're actually very nice. They're easier to optimize for good performance. They're useful for low-level feature extraction. People also use them on audio processing. The disadvantage is you can have a high number of computes to get very good results. And the other disadvantage is that you have to consider fixed input frames, so it's not always ideal in audio. And recurrent neural networks are nice because they naturally consider time, and you can run them online continuously. And they also give very good results on tasks involving temporal sequences, as the last speaker showed. And the disadvantage is that they use a very high number of parameters, which could be a bottleneck. And so now I want to show some examples on how we have benchmarked these different DNN types on a particular task. In this case, it's an environmental sound classification task. It's on a data set called audio set. We took a subset of it, and they have a number of different classes. Here we recognize things like engine, gunshot, dog, etc. And as you can see, the results that I show is done on a frame of 25 milliseconds with a stride of 10 milliseconds. And this is done for 3 different architectures, or 3 different models, the MLP model, the CNN model, and the RNN model. Now, the RNN model also has layers, convolutional layers beforehand, because that helps you to get very good low-level features. But what we try to keep here is to have a very similar accuracy between all these 3 models. And you can see from the number of parameters that you need and also the number of operations that you need is that the MLP has the highest number of parameters, CNN has the fewest, RNN has a lot, but the number of operations that you need is not so different between all 3 of them. And so the RNNs trade off parameters for accuracy. So if you want a very accurate network, then you want to go to an RNN, but if you can trade off for, because you don't have enough memory on your device, then you can go for a CNN. So now in terms of hardware, now we're talking about ASICs, right? So if you know what the network is for the task that you're interested in, then you want to build an accelerator. And so for audio, it's not just the low power, small footprint memory compute trade-offs that you have to think about. You also have to think of the analog front end, right? Because the waveform coming in has to be converted into audio features. And sometimes that costs more than actually running the network itself. And then the other thing is, what do you do now? So I gave you a whole list of TinyML tasks that are interesting. Do I build a chip for each one of these tasks, or do I build a chip that supports multiple tasks? And so the pipeline usually that you see in different circuits and systems communities is that you do something as follows. So you have a block that computes the features. So this is the analog front-end features. And then it goes first to a VAD, a voice activity detector. And that makes a lot of sense because that means you don't compute all the more expensive blocks unless there's a speech that you recognize. And so now you use the VAD output to gate the activation of any of these blocks over here. Usually it's the speech enhancement that comes so that you can clean up the speech before you do the keyword spotting, speaker verification and recognition. And if you take results, say, from one of the ASICs, for example, in this case, it's a DNPU from Professor Liu's group. We took the power efficiency numbers that were reported in the paper. Oh, sorry. I think I'm... Then in this hierarchical way of processing, the amount of power that you add for each of the tests that you include is going to go up, right? Depending on if you start from the VAD, then if you add speaker verification, it's going to go up, speech enhancement, and so on. So basically, every test that you add on is going to go up to, if you have all 5 of these tests running at the same time, it'll go to about 10 milliwatts. So this is going from 10 microwatts to 10 milliwatts is kind of an average because there are ASICs out there, of course, that burn a lot less power than the 10 microwatts. In fact, if you at ISCC, they actually also report ASICs that burn on the nanowatt level. Okay, so this is just an average. And these power numbers sometimes could be misleading, and so this is what I want to talk about: is that these numbers don't include system level power, right? So you can't run the ASIC on its own. You need a lot of stuff around it so that you can actually operate the device. And so this is what I want to talk about next. So the first thing is that we look at kind of benchmark results from running audio TinyML on embedded hardware. And so in this case here, we're looking at speech enhancement. And what you do here is, for speech enhancement, is you create noisy speech from, you actually convert noisy speech to clean speech, which means in this spectrogram picture, you learn a mask for the speaker, and then you apply it to noisy speech so you can get the clean speech. And so this mask here is generated by a network. And we train different types of models for generating the mask. So we have convolutional networks that have different types, 2 different types. We have an MLP model, and also we have a RNN LSTM model. And the 2 different convolutional models basically have a different number of stages, and these are dilated DNN models. And so the next thing that you see in the table here is something called span. And so this is the receptive field input of the model. So it's what the model uses to make a decision to generate the mask. So you can see it's almost a second for you to get very good results. If you want to have even better results, then you can get that by increasing the span of the model. MLP, basically, it's just a single frame. And then for the LSTM, you can consider it, anyway a long time history. And so the runtime on the Raspberry Pi is about 315 milliseconds just to run this network. And so 350 milliseconds equates about 3 hertz, right? So this is actually kind of not good for audio, right? Because we just said that we would like to listen to the sound in 15 milliseconds. So here, in this case, the network actually is the one that increases the latency more than what you would like. The MLP and the LSTM, you can see they're not so bad, but they have numbers very similar to the CNN. And the number of parameters, again, for CNNs are much lower than the MLP and the RNNs. And if I look now at the memory that's used on the Raspberry Pi, so this is the overall dynamic memory usage, you can see that for the second CNN model, it's very close to the LSTM or RNN model. Okay, so anyway, it gives you something to think about which of the models would be better. And the next example that I have here is doing a small vocabulary continuous speech recognition, and now doing it on the FPGA. And so this particular platform, this model we call EdgeDRNN. So it's meant for the Delta Recurrent Neural Network, which is a variant of the RNN that we developed within our group, where we actually take advantage of temporal sparsity in computes. And so it helps you actually cut down on the latency when you actually have to run the network. So you have, for example, if somebody says a 1, then you want to produce the label 1 on the output. And this network has been trained on the TI digits data set. And just so you have an impression of how much it actually costs to run this accelerator. So it's a one, so we've tried different model sizes. So it's either a one layer 512 neurons or two layer 512 neurons. But in this case, it's a two layer 768 neurons. And so if you run it on this FPGA, which is a mini Z SoC, which burns about 2.4 watts, if you look closely, you can see that the accelerator only burns 3.6% of the whole system power, right? So what this is saying is that even if you could reduce the power of the accelerator, right, it might just only be a tiny portion of all the stuff that's needed around it so that you can actually operate this device, right? So you can see DRAM actually costs quite a bit, and it could be your network needs to go on DRAM, right? And then there's also the processing system itself, which burns half of the system power. So actually doing this kind of benchmarks, even on embedded systems, is actually good for you to understand how what the architecture should be of the accelerator that you want to build later. And so we also did this analysis where we looked at the word error rate of the model on the TI digits data set as a function of the number of operations. In this case, it's actually increasing the number of parameters. And so you can see, again, the word error rate drops as you increase the model size. And of course, because you're increasing the model size, you're going to spend more energy for each frame that comes in. Okay, so there's a trade-off. And in terms of latency, well, you can see actually the latency is also grows as the model size increases. And the throughput that you see here is really just the throughput of accelerator. So in the end, this is the max that you're going to get out of it. And the thing to notice is that these latency numbers are actually quite low if you consider the fact that each frame of your audio is about 25 milliseconds. If you do a stride, it's also it's in the order of 10 milliseconds. So actually this network is actually very cheap to run. Okay. All right, so in conclusion, so hopefully I've shown you that there is actually a variety of possible architectures for TinyML audio. The size depends on the complexity of the task and also the resource that your hardware has. The architecture type depends also on the amount of memory compute needed. You can use the different methods that have been suggested by the previous speakers so that you can get to the right architecture type. And there's going to be always this trade-off between power, accuracy, latency, memory, and compute requirements, and also the tasks that you want this network to do. And so I think there's still a lot of room to improve on kind of the networks that are out there for doing TinyML. But there's already a set of networks that you can use to start off with that I believe can bring, so if you go to the ASICS totally, you can actually bring down these energy numbers that I showed from the FPGA. I'm pretty sure you can bring down by at least, I want to say 10x, but even 100x if you know what needs to go around it. Okay, and finally is to acknowledge the people in the census group, especially the ones that contributed to the work that I showed here. And also there's a set of references in case you need to look up some of these numbers that I showed in the slides. Okay, thank you.
Thank you, Shih-Chii.